Hi, welcome to lecture number 46. This is on subsurface drainage design. So, in this lecture we are going to we are going to estimate the steady state flow of drainage water to the drains. So, in this we are going to derive an equation using Hoogout formula we call. So, seeing the steady state conditions. Okay. So, next is before going into the details to the drainage design principles. So, the basically is the drainage design whenever we are talking. So, it should require developing some criteria. So, the drainage design should specify the operation of the system and the physical configurations that fulfill the drainage objective. So, you have to see what is our drainage objective, whether to dispose the excess water on the surface or to remove excess water from the root zone as well as the salts. So, based on the objective you have to specify those objectives. Okay. So, then consider the irrigation and drainage systems as integrated water management system. So, the drainage system should be in such a way that it should integrate with the irrigation management, okay, and minimize depercolation loss through improving the water management system. So, water management through water management, the drainage system should be able to minimize the depercolation. And then they characterize the establishing the water table depth at the midpoint between laterals and drainage coefficient. So, your drainage system should be able to equate the water table depth from the top surface at the midpoint and the drainage coefficient. Okay. So, midpoint, laterals and the drainage coefficient. Okay. So, that means in a day the amount of water which is resulting from the drains. So, that is drainage coefficient that should be equate the depth to water table at the midway. Okay. And the specify option regarding reuse of drainage water. So, whether the drainage water needs to be reused back as irrigation water or not. So, that also needs to be specified. So, these are the main basic things we need to consider before designing a drainage system. Okay. So, then the next is there are the steps we need to follow in designing the drainage system. The first one is the investigation. So, we need to investigate the things like soil profile, geohydrologic and groundwater quality. So, these things needs to be understood before installing or before planning a drainage system. So, soil profile. So, whether it is layered soil or clay soil or any like sandy soils, all those things, and geohydrologic. So, geohydrologic in the sense the hydraulic conductivity at different places, different depths and the quality of groundwater, and measuring involves the quality of proposed irrigation water. So, you need to check whether the quality is okay to artificially irrigate the plant or not, and estimating the surface the sources of drainage water other than irrigation. Are there any other sources of drainage water other than irrigation, and reviewing and analyzing the climate data of the area is very much required in order to understand the peak discharge from the particular area, and selecting appropriate crops or cropping pattern. So, and what kind of crops you are going to grow in that land which is after drainage. Okay. So, this also then after that the next step is selecting appropriate cropping pattern. So, that and then you have to measure the hydraulic conductivity and root zone of the soil based on the particular soil type, and the drainage coefficient, which is the amount of water which is being drained from the area in 24 hours. So, that is drainage coefficient, and optimizing drain depth and placement of lateral drain. So, once all these things are done, so you need to optimize the drain depth, that is the top to I mean drainage I mean from the soil surface, how deep you are going to install, and also the spacing between the drains. Okay. So, here if you see the two ways, drain depth is specified, you can specify drain depth, and the spacing is calculated based on the recharge schedule and the midpoint water table criteria. So, here the first fix I mean for the drain depth, and then you have to iterate length, for which you get the equal length for each iteration. We are going to see these calculations. And the drain depth is varied. Now, the drain depth is changing, and calculate the range of depths and spacings, and economic analysis performed in this case. So, you get a combination of drain depth and spacings, and you will be deciding based on the I mean economic criteria which depth or which spacing needs to be I mean decided. Okay. So, the next is once the drain depth and drain spacing is decided, then the lateral pipe size and main pipe size or needs to be decided. We discussed this in the previous lectures, the drain pipe sizes, and then after the drain envelope material. So, you need to find out the drain envelope material, which is generally greater than 10 times hydraulic conductivity of the soil material, and after that you have to design the drainage disposal system or reuse drainage system. So, whether then you have to design the drainage disposal system, whether you need to dispose the drained water, or if you are going to reuse that system back to the irrigation system irrigating the crop, then you have to design the drainage system for reuse purpose. And then finally, the design the pump size and pump maximum drainage discharge from the field. So, once the drainage water is coming to the main ditch, right. So, then the outlets come into the picture. So, whether you need to pump out or the gravity outlet. So, those things, and basically there is a note, the United States Bureau of Reclamation so recommends installation of drains at a depth of 2.4 meter if possible, to provide a balance between the system cost and spacing. So, that is what USBR found, the 2.4 is ideal for a cost effective drainage design, drainage system design. So, then after that how to calculate the drainage coefficient using the water balance equation. So, for example, here estimating the drainage requirement or drainage coefficient. So, for the drainage requirement or drainage intensity or drainage coefficient, we also call different names, drainage intensity, drainage coefficient. So, these steps may be followed. The first, collect the long term rainfall and other weather data for the project area. So, this is the number 1, and number 2, calculate the daily average rainfall, evaporation and evapotranspiration rate for the targeted crop season. Okay. So, the ET is estimated, and the R, the average rainfall, and average P is the precipitation. Okay. So, R is the surface runoff. So, then using the water balance equation, D is the drainage. So, the drainage is equal to P minus E T minus R. So, I mean generally if you have the drainage system here, right. So, this is drained water, and this is precipitation, and this is R, rainfall, and if you have a crop, then there is a E T will be taking place. Okay. So, using this balance, water balance, so D will be estimated, D is equal to P minus E T minus R. Okay. So, since we are balancing for daily, so D will get the drainage water per day. So, that will be equal to the drainage coefficient. Okay. And then the next is drain spacing. So, the drain spacing basically the drain depth and spacing should be such that the water table midway between the drains remains below the root zone. This is the, so as I mentioned in the beginning of the slide. So, the basic the basic in the criteria in so in the basic criteria in selecting the depth and spacing is, so in the midway, if you see the midway, okay, so this is the D and of course, this is H. Okay, so this is basically the water table, the root zone depth, let us say Z. This is we are interested in. So, the drain spacing, whatever we are giving drain spacing and drain depth. So, drain depth and the W and drain spacing, this is L. So, this will be decided in such a way that in a day, so this much area, so this area needs to be drained off. Okay, this needs to be drained off. So, this is the criteria in following. So, deeper the drains, wider spacing and less is the number of drains. So, this is okay, you can go deeper, right. So, you can go very deep, right, and so that will allow keeping the drains in wider spacing. So, that you can save some money, because earth working and everything will be minimized, and also the number of pipes, number of laterals. So, that will be reduced. So, and that is economical. Okay. So, but the depth and spacing of subsurface drains, it basically depends on the hydraulic conductivity of soil and the crop to be grown and outlet condition and agronomic practices. So, all these things needs to be considered before deciding a drain depth and a spacing. So, the drain spacing formula, it could be like a steady state condition and unsteady state condition. So, in the previous lecture in the last week, we were discussing the steady state condition. So, what are the things during steady state condition? So, the main assumption here, steady state rate of recharge to the groundwater will be equal to rate of discharge through the drain pipe. So, the rate of recharge which is taking place, let us take Q. So, that will be So, that will be equal to the drain discharge. So, there is a Q and this Q. So, this will be equal in this case. Okay. And hydraulic head, the height of water table between drains remains constant. So, H is constant, the same thing if you see the H, which is here. So, this is constant in case of steady state condition. Okay. So, the Q is recharge and Q, this is drain flow. So, this is one assumption, the next one is H is constant. Okay. And in the steady state, the other assumptions are like the soil is homogeneous and isotropic. Okay. So, then in case of unsteady case, the terms are vary, like a rate of recharge varies with time, flow of groundwater towards the drain is not steady. So, these things we have already discussed in the previous week. And then for the steady state formula, steady constant flow occurs through the soil in drain, the discharge equals to recharge, H is constant, right. So, here, so let us say this is the Q and this is the Q. So, Q is equal to Q and H is constant, okay, in case of, whereas unsteady all are going to change, like this Q is going to change and the drain discharge is going to change and H is going to change under unsteady state condition. So, the procedure also we explained last class, like knowing small q, that is a drain discharge, and H is the suppose this is H. Okay. So, H is the root zone, you can say root zone depth, W is the drain depth, and you can estimate H, which is equal to capital W minus capital H, right. So, and then So, knowing the soil parameters like hydraulic conductivity, right, and drain type. So, what kind of drain is a tile drain or ditch, drain space formula will be used, and finally, L will be calculated. So, this is the way the schematic of for finding out drain spacing. And here this picture so clearly shows the assumption this is the real field and the schematized field for modeling purpose. Okay. So, if you see there is a vertical flow is taking place initially and then towards the drain, this is the way the radial flow goes, whereas for making the modeling simple. So, the vertical flow and then horizontal flow and then radial flow, vertical flow, lateral, radial, vertical, horizontal and radial. Okay. So, this way and also the horizontal flow is influenced at L by 4 distance, and then the radial flow is influenced 0.7 d from the drainage base. Okay. So, the Hoogout formula here. So, this is based on Jupit-Froschmeier assumptions, right, Froschmeier assumptions. So, assumptions are Hoogout's formula can be summarized as follows. The soil is homogeneous and isotropic. So, that means the aquifer properties or soil properties will not change in the distance and the direction or the time. So, and Darcy's law is valid for water through soil into the drain because it is completely saturated condition. So, the Darcy's law is very well valid for the Hoogout assumption, and an impermeable layer underlies the drain. So, always there is an impervious layer which underlines the drain. Okay. And then the hydraulic gradient at any point in the flow regime is equal to the slope of the water table. So, hydraulic gradient that is dH by dx, right, dH by dx at any point it dictates the flow regime. So, it dictates the flow process or flow direction. The diameter of the drain is small compared to the saturated thickness below the drain. So, whatever the diameter of the drain, so this will be smaller than the saturated thickness. Okay. So, that is a thickness of the aquifer. The drains have no entrance resistance. So, the entrance resistance we are considering 0. The flow through drain is full half full. So, at least half full we should maintain, right, in the drains. Okay. This is half full, we need to maintain the drains. Okay. So, based on the assumptions, only head loss due to horizontal and radial flow to be pipes are considered. So, since it is we mentioned this is steady state, right. So, basically H is equal to H V plus H H plus H R plus H E, right. So, H V and H R we are neglecting here, right. So, assuming the I mean based on the Hoogout assumptions. So, now H is equal to H H plus H R, that is head due to horizontal flow and head due to radial flow. So, this is the one, and so this is for H H. So, we have defined or derived this equation in the previous lecture, and whereas H R. So, this is from N's equation, this is also we have shown in the previous week. So, combining these two, so we will give the head at the, so you get head at the at any point from the drain space. Okay. So, this one. So, Hoogout conceived that the parallel open ditch system with the ditches reaching to the impermeable substratum could generate the same Q for the same water table head H as an identically spaced pipe drain system by reducing depth d to the impermeable stratum. So, here the in order to make the open ditch system, right, to a pipe drain system, or the pipe drain system to open drain system. So, what he assumed is, so for the same hydraulic head, and from same discharge, right, from the discharge can be possible when the pipe drain is installed at the impervious layer. So, this how it is achieved by reducing the d to an equivalent depth small d. Okay. So, if you remember here, right. So, this is impervious surface in actual case. Okay. So, and this one is the capital D, this is the capital D. Okay. So, here this is a small h. Okay. So, the pipe drainage system can be converted or converted into a open ditch system, right, by putting this drain to the, by assuming that this pipe drain is exactly sitting at the impervious surface. Okay. And then h won't change and q won't change for the same h and q, right, sitting up. So, how it is possible? So, this when you put it in the down, right. So, the depth here is no more capital D, that will be equivalent depth d a. Okay. That is equivalent depth d a. We are going to see that. So, that means, see, for making this you can completely eliminate the radial flow. So, it is now completely the horizontal flow. Okay. And so, here, so equivalent flow, so basically the horizontal flow. So, h is equal to, which is horizontal equivalent, q is equal to L h square by 8 k into d h star. Okay. d h star is equivalent depth. So, since d, the small d is less than capital D, okay, the small d is less than. So, this is open ditch and this this is the pipe drain, and you are converting that into open ditch system. This is open ditch system. Okay. If you see this, initially this is impervious surface, and which is the drain is installed at d distance from the impervious surface. Okay. And then h is the height of the water table, okay, from the drain base. So, here in open ditch system, so this is in imaginary impervious layer, okay, imaginary impervious layer, and this is the capital D. Now, small d which is less than the capital D. So, since d is small than less than capital D, h is greater than h h dash is greater than h h. Okay. So, why? Because if you see the equation, so when d is getting smaller, h is going to bigger. So, then d h star will be equal to d plus h by 2. So, this is another assumption. So, d plus h by 2. So, h, half of the h will be the original capital D. So, putting the value small h is equal to q into L square, right, q into L square divided by 8 k into substitute d star h here, right. So, then finally, you will get q is equal to 8 k d h by L square plus a 4 k h square by L square. Okay. So, here if you observe clearly, the horizontal flow takes place partly below the drain base. So, here h square, so this is above the drain base and this is below the drain base. So, the horizontal flow is taking place. So, not only the horizontal flow is taking place, so above the drain base, so and below the drain base. So, above the drain base as well as below the drain base. So, these two parts horizontal I mean flow to the drain is taking place. So, then if the both zones have a different case, suppose you have, this is the drain base. So, below the soil you have k let us say K2, and above soil you have K1, right. So, it has a 2 soil layers. Then Q is equal to 8 K2 dH by L square plus 4 K1 H square by L square. So, where K1 K2 are the hydraulic conductivities of the bottom layer and top layers. Okay. So, d whereas small d is given or estimated as small d is equal to capital D by 8 capital D pi L ln of d by u plus 1 when d greater than L by 4, and for d less than L by 4 you get small d is equal to pi d by 8 ln by L by u, where u is the wet entry perimeter of the drain. Okay, we are going to see how to calculate the wet entry perimeter. So, that means, so with this equation and with these conditions you can estimate the L value, but remember here if you see, so here in this equation, so the same equation can be written like L square which is equal to 8 K2 dH by Q plus 4 K1 H square by Q. Okay. So, here L is a function of D, okay. L is a function of D, but here D is a function of again L. Okay. So, if you see in this equation D is a function of L. So, that is why this is an implicit equation. So, we will be calculating this is the implicit equation, we have to use trial and error method for calculating the drain spacing here. Okay. So, in the Hoogout equation, so this in the previously explained, so you can turn this equation into Q is equal to 8 K dH into if suppose both layers have the same Q K, then this is the equation. Horizontal flow above the drain level. So, this is because it does not contains any D term which is supposed to be the depth below the drain base. So, this represents the flow above the or horizontal flow above the drain. So, since it contains D, so this is the flow which is below the drain. So, this again combines both horizontal flow at above and below drain base. So, using Hoogout formula, the process for determining drain base. So, already explained, the first thing is formulation of basic design criteria Q and H, right, and then you can find out small h and soil parameters like K and D, okay, and selection and also for pipe you get U drain type based on the pipe and envelope you get this U, and determine you get use Hoogout equation and find out L value. Okay. So, the solution of Hoogout formula is either trial and error or graphical solution. We are going to see that how the trial and error and graphical solution can be done. Here the trial and error equation, since L depends on small d and D depends on capital L, the Hoogout equation is implicit equation, and if you see this, so this is the way for first we have to assume some initial guess L, right. So, knowing the L, find out capital D, okay. And for the knowing the L and a particular drain space like capital D, right, and you will be deciding which formula needs to be used to find out small d. So, once you know the small d, go back to the Hoogout equation and you can find out new L, that is L dash, and you can compare this L dash with the previous L. If these two L's are closer, so then your spacing is correct, okay, and all other parameters are a very good guess. Okay. So, here solve the Hoogout formula L, compare the value with the assumed L and modify the value of L and repeat the steps until the calculated assumed value are equal. Suppose if these are not equal, right, if these are not equal, and you are going to change this initial guess L, okay, this initial guess L, and then repeat the steps and find out new L dash, right, and again compare the previous L and the calculated L. So, these steps needs to be repeated until these two L's are closer or almost equal. So, there is a graphical solution also available. So, since the Hoogout equation contains two terms, so that is 8 k 2 h by q and 4 k h square by q. So, in the two graphs are available based on the length. So, graph A for L equal to 5 to 25 meter and graph B for L equal to 10 to 100 meter. So, based on the assumed length, so you can go ahead with these two graphs. So, here y 1 axis contains 8 k 2 h by q and y 2 axis contains 4 k 1 h square by q. Similarly, in the other graph the same things. Okay. So, first calculate 8 k 2 h by q for example, here, and similarly calculate other term and combine these two things. Okay. And for a particular d, so these d values are given, right, for a particular d. So, identify knowing the d value, right, you can find out the corresponding or interpreted. So, for example, this is the value 8 k 2 h by q and 4 k 1 h square by q you calculated and you located 2 points here, and let us say d is equal to for d is equal to 3, this is the 3. Okay. So, the corresponding L value you need to calculate, I mean this is the L value. So, now L is equal to some 33 or something like that. Okay. So, now L is equal to 33 meters. So, this graphical solution is easier, right, compared to the previous calculated analytical solution. So, in this lecture we observed the design criteria, design principles, and what are the steps involved in designing subsurface drainage system. Then the Hoogout assumptions and the Hoogout formula. So, since the Hoogout assumption for making the horizontal flow, so mainly the Hoogout basically assumed the tail drainage system to be a open ditch system by taking the tail drain to the impervious surface and finding out the equivalent depth. So, he has given the formulas for calculating the equivalent depth d value based on the length and drain space drain depth, okay, based on these two things. So, and Hoogout formula and these two conditions will be helpful in finding out the drain spacing by following either trial and error method or using a graphical solution. Yeah, thank you so much.